Now, before we broke off, we discussed this very important theorem called the principle of minimum potential energy, which applies to all linear elastic solids. What it says is the following. Take a huge bag full of the infinite number of admissible deformation fields, which we have called ui hat, that satisfy the essential boundary conditions on delta VU, which is the part of the boundary on which displacements are specified. So these admissible displacement fields have no property other than the fact that they are continuous fields, and they satisfy the essential boundary conditions, that is the displacement boundary conditions, wherever displacement boundary conditions are specified. Apart from that, they are completely arbitrary, but since they are continuous, then we can differentiate them and find a admissible strain, which we called epsilon hat. Now, make up the potential energy of the system, the whole body, with these admissible deformation fields and the admissible strain fields that we have obtained from them. So this is the total strain energy stored. This is the potential of the body forces, and this is the potential of the surface tractions. And the strain energy minus the potential of the applied loads gives you what is known as the potential energy. And the potential energy is calculated, the strain energy is calculated in case of a linear elastic solid by remembering that sigma ij is equal to del u del epsilon ij, where u is a function of the strains, and therefore u can be written as sigma ij d epsilon ij, and integrating that over the volume, you get the total strain energy stored. So this is the strain energy per unit volume. This has units of energy per unit volume. Integrating it over the volume gives you the total strain energy. This is the work done by body forces. So take a small element dV, and the body force on it is Bi, is the total force on it is rho Bi, and the work done by it is rho Bi times Ui hat. This is a repeated index, so it is rho B1 U1 plus rho B2 U2 rho B3 U3. Similarly, integrate that over the entire volume, you get the total work done by the body forces. Integrate the traction work over the entire surface. Actually, you have to integrate it only over del Vt, because that's where the tractions are specified. You integrate this and you get the total work done by the surface tractions. So this gives you the potential energy, and the principle of minimum potential energy states that from these bag of infinite number of admissible deformation fields, the minimum value of this quantity, the potential energy, will be obtained when U hat is equal to the actual displacement field. The actual displacement field is the solution to the elasticity problem. When you hit upon the actual displacement field, then pi will be a minimum, which means this gives us an alternate way of looking for a solution to a problem in elasticity. Instead of solving the set of differential equations, which you might remember are for statics, these are the equilibrium equations, these are the strain displacement relations, and then you have the constitutive equations. So these set of 15 equations, you can solve them for the stresses, the strains, and the displacements. You can do that with the boundary conditions that are specified on delta VU and delta VT. That is one route to solving a problem in elasticity. This is an alternate route. We can take the principle of minimum potential energy, calculate the potential energy, and minimize the potential energy to find the U that minimizes it, or to find a u hat that minimizes this potential energy. Now, here is a problem. How do I minimize this? U hat is actually in general a function of x, y, and z. So how do I find a function that fits in here and minimizes this whole quantity? So that is what we are going to turn to. That is the problem of variational calculus, and we will now turn to that to see how a function which is a function of another function is minimized. How do I find a function that minimizes a particular function of a function? So that's going to be in the next installment.